Hi everyone, welcome back. Today we'll talk about the diagonalization of matrix and we'll understand the theory with the help of one example. So here is an example. It says find the similarity transformation that diagonalizes the matrix A, and we are given with a matrix A. So in case of diagonalization, there can be a lot of questions in different forms. They can ask just diagonalize matrix A, or they can ask check whether matrix A is diagonalizable or not. They can ask find the transformation that diagonalizes matrix A. They can ask find the similarity transformation, as they have asked in this particular example. Okay, so the steps that are involved in solving such kind of questions are same. There is no change. So let's go to the solution and just check what are the steps involved. Whenever you see such kind of questions, the first thing that you need to do is find the eigenvalues of the given matrix. So we are given with the matrix A, so we need to find the eigenvalues of the matrix. To find the eigenvalues of the matrix, we need to find the characteristic polynomial. And in order to find the characteristic polynomial, you need to solve this determinant here. So we have solved the determinant by following step. You can just try to solve it yourself and compare the steps. After solving it, we got our characteristic polynomial as this: lambda plus 3, lambda plus 3 and lambda minus 5. Okay, now as we know that the roots of the characteristic polynomials are the eigenvalues of the matrix, right? So we need to find the roots of the characteristic polynomial. So here we are finding the roots of the characteristic polynomial. We have equated this determinant to 0, and now we are finding the roots of the characteristic polynomial, and we found out the roots as minus 3, and 5, right? So the eigenvalues, distinct eigenvalues, are minus 3 and 5. We have two distinct eigenvalues, right? Next thing that you need to do is look at this condition. You should always remember this condition, right? This is very important. Whenever you will be solving a diagonalization question or a question that is involving some sort of similarity transformation related to diagonalization, then you will have to make sure that the algebraic multiplicity of each eigenvalue is equal to the dimension of the eigenspace created by the eigenvectors corresponding to the eigenvalues. Okay, so it may seem like it's a difficult statement here, but let me just explain you few terms. Okay, let's take this algebraic multiplicity first. So when we said that we have two distinct eigenvalues, in our case we have minus 3 and 5, and we know that minus 3 is repeating 2 times. So the algebraic multiplicity of minus 3 will be 2. So it is nothing but the number of times our eigenvalue is repeating. Okay, so algebraic multiplicity is the number of times the eigenvalue is repeating. So if we have, say, let's suppose that the roots are like 2, 2, 2, 5, 5 and then 1. Okay, so the algebraic multiplicity of 2 will be 3 because 2 is repeating 3 times. Algebraic multiplicity of 5 will be 2 because 5 is repeating 2 times. Algebraic multiplicity of 1 will be equals to 1 because it is not repeating, right? So if the algebraic multiplicity of each eigenvalue of the matrix A is equal to the dimension of the eigenspace created by the eigenvectors corresponding to the eigenvalue. So eigenspace is nothing but a space created by the eigenvectors that are obtained by the eigenvalue. So it is not necessary that if we are having two distinct eigenvalues, then we will have two eigenvectors. If the multiplicity of one eigenvalue is more than 1, then we can have multiple eigenvectors for that particular eigenvalues. Like in our case, we'll see that for minus 3 we have two eigenvectors, and linearly independent eigenvectors corresponding to the eigenvalue form the basis of the eigenspace. Okay, so what is eigenspace? Eigenspace is nothing but a space created by the linear combinations of the linearly independent eigenvectors corresponding to the eigenvalue. Okay, it may sounds a little bit difficult, but if you are not getting it, just ask me directly. I'll try to explain it in more simpler way. Okay, or you can just read it. It is, I guess, more clear. Maybe you're getting confused, I don't know. Just write the comments, I'll be replying to them. Okay, so now we know that the algebraic multiplicity should be equals to the dimension of the eigenspace created by the eigenvectors corresponding to the eigenvalue, right? And this should be true for all the eigenvalues of matrix A. Okay, so now let's find the eigenvectors. Find the eigenvectors corresponding to the eigenvalues. So first we are taking our eigenvalue -3, and the usual expression that we used to use to find the eigenvectors is there. And after that, you know what to do. You need to just simplify it, and after getting this matrix here, you need to reduce it to Roeclian form. So we are reducing it, and now we got this. And after that, we need to obtain the equation. And then we can assume, because there are 3 variables, so we can assume 3 variables and 1 equation. So we can assume the value of any 2 variables. So I have taken z is equals to 1 and y is equals to 0. z1 equals to 1 and y1 equals to 0. And we got x1 equals to 3. So corresponding to these assumptions, I'm getting this 1 eigenvector. So this is 1 here. Okay, and after that, again I have took some assumption, this time different one, and I got another eigenvector like this. So I have taken z1 equals to 1, z1 equals to 0, y1 equals to 1, and I got x1 is equals to -2, and I got this eigenvector. So, and you can see that v1 and v2 are linearly independent. You can check the nature of these 2 vectors. They are linearly independent, and we know how to test the linear independentness of 2 vectors. So basically you can just write it like alpha 1 v1 plus alpha 2 v2 equals to 0, and you can find out alpha 1 and alpha 2 if all these all these alpha 1 and alpha 2 are coming to be 0 in order to satisfy this condition, and you are not getting any other solution for alpha 1 and alpha 2, then you will say that these 2 vectors are linearly independent, and you can check it. Now using the same methodology, we can find out that corresponding to lambda 2 equals to 5, we have our eigenvector, that is -1, -2 and 1, right? So this is your work, you find it out. Okay, and now we can see that this v1 and v2 we found corresponding to our lambda 1 equals to -3, v1 and v2, here v1 and v2 corresponding to lambda 1 equals to -3 form the eigenspace. Okay, and this eigenspace, because these 2 vectors are linearly independent, so these 2 vectors will form the basis of this eigenspace, and the dimension of the eigenspace will be the number of linearly independent vectors that are present in the basis of eigenspace. Okay, so the basis is this of this eigenspace. The basis is v1 and v2, and we have 2 linearly independent vectors in the basis, so the dimension will be nothing but 2, and the algebraic multiplicity of our eigenvalue is 2. So we can say that the condition that is required for the diagonalization of matrix A is satisfied for this lambda 1 equals to minus 3. Okay, and this also follows for lambda 2 equals to 5, because there is only one vector and the algebraic multiplicity of lambda 2 equals to 5 is also 1. So all the eigenvalues are satisfying the conditions, satisfying the condition that is required for matrix A to be diagonalizable. So we can say that matrix A is diagonalizable. After you checked whether the matrix A is diagonalizable or not, and you got your answer in affirmative way that matrix A is diagonalizable, then how to find this matrix P? Let's see. So it is very simple. Basically, to find matrix P, it is very simple. Just place the eigenvectors that you found as column vectors of P. Okay, so we placed eigenvectors. This is v1, this is v2, this is v3. So I have not used these notations when I was solving for the eigenvectors, but just understand that these are the eigenvectors. So you can place the eigenvectors, and after placing the eigenvectors as column vectors, you'll get a matrix that will be matrix P, right? And then find the P inverse, and after that you know now P inverse, P and matrix A, and so you can easily find the matrix D, right? And this whole representation here will be the similarity transformation that diagonalizes the matrix A to D. I hope you understood the concept and what are the steps that are involved. Make sure that you remember this condition here, because it is very useful, and whenever you will be solving questions related to diagonalization, you will be using this condition again and again. So make sure that you remember this condition, and if you are having any doubt related to this condition, you just comment down and I'll be answering to that. Okay, thank you for watching. If you have any other query, you can just write down in the comments and I'll be solving those queries. Thank you so much for watching. Subscribe to my channel. Bye.